Right. It's time to start. So, yeah, we don't have a herald, so I'll be heralding myself. Hello. Our next speaker will be Daniel, also known as CyReVolt, and he will be talking about patterns that are hiding in DRAM initialization. Hi, I'm Daniel, also known as CyReVolt, and I will be talking about DRAM initialization today, and especially patterns hiding therein. So, we're going to talk about a few things here. This is the very rough agenda. I will give some background knowledge, introduce the topic itself, give some history of how I got into this topic myself, and then I will be showing how you can translate code that is unfortunately only available in binary form, and that's where we're going to look at certain patterns. So that will be the main part of this talk. Then I will briefly skim through how you can approach understanding this thing wholly in a way, but yeah, it's not going to be very detailed because it's a very, very broad topic, unfortunately, very deep. We will see that later, and then I will give some further ideas and hints if you also want to get into this. So let's start. Some background knowledge. We're going to talk about a bit of computer knowledge now. And the problem with computer knowledge is computers are very, very complicated and complex, so it's actually very, very hard to learn all that stuff and even harder to actually pass it on because, everybody is a bit different, everybody starts at a different point, and so on. At the same time, there is a bunch of information that is also very, very hard to get out of, vendors, for example, that do not want to disclose their information, and that is one issue I constantly run into while doing DRAM initialization. But yeah, the thing is, there are some people who actually understand the stuff. Those are the so-called domain experts. I'm not a domain expert in DRAM initialization. I'm a software engineer, so my domain is I can actually recognize code and its behavior, whereas domain experts can understand what it's about. So, they can tell you, oh, this is doing this and that very, very specifically, and I can tell you, what the, general approach is from, a software engineering standpoint. We're going to talk a bit about platforms now, because that is the broad topic in a sense. And if you look at Wikipedia, you will find, this sort of semi-definition here of a platform. Essentially, it's saying it's an environment where you can run software, and that can be any sort of layer in a way. It can be direct hardware, it can be an operating system, it can be a web browser, sort of everything. There is one thing missing here, and that is firmware. For some reason. Anyway, so there is actually a very, very big gap in that space, and that's why I started another project, which is called the Platform System Interface Project. And in that project, you can visit the website. You will see the slides later, so you can also click all the links if you want. I'm trying to summarize how hardware platforms work in a very, very general way, and how they transition to something that is, like an operating system, things that you use every day in a way. But yeah, there is actually a lot of stuff going on in between, and yeah, there is not many experts, unfortunately, in that domain, so I want to pass on that knowledge so that we get more experts. That's roughly how I do it. I look at all the things, I extract whatever features I understand from it, I document that, I reiterate over that stuff, because over time you always figure out, oh well, you can actually describe this in a different way or something, right? So it's a very, very tedious effort actually, and yeah, I'm very, very slowly getting there. So yeah, the thing is, I actually wanted to develop firmware myself, and so I had to struggle with that myself, right? And the problem is, firmware itself even is a very, very complicated term again, because everybody has a different understanding of it, unfortunately. There is no very clear definition. Some people say, hey, yeah, it's the BIOS, and that even is meaningless by itself, because it's been reinterpreted 100 times already. There are some people saying, well, firmware is software that is hard to get to. That's also a definition I can very much identify with, because it's often the case. But I mean, if you visit events like this one here, you know that there is always people who figure out how to get to it anyway. But yeah, that's not today's topic. Then, colloquial speech marketing, if you talk about this stuff with ordinary people, they would probably just be confused. It really takes a lot of time to get into this. this is my definition here, and this is specifically the kind of firmware we're talking about today. I'm saying firmware is the very, very essential part that brings up a hardware platform into such a state that you can run an operating system on it. And that can be any sort of scope in a way. But yeah, the very, very minimum part is very much the DRAM initialization, today's focus. This is what you can think of that. Imagine you turn on your computer, you cannot actually use your DRAM, right? By the way, if you don't know what DRAM actually means, it's the dynamic random access memory. There is also static random access memory. That is the memory that you can use right away when you power it on. But it's very expensive to make. So in order to have the many gigabytes of memories that we have now, we actually do DRAM, and that unfortunately needs a lot of initialization first. This is how Intel approaches this stuff. So if you have an Intel-based laptop like this one here, for example, you would commonly find firmware that is based on their so-called FSP. They call it the firmware support package. It's a bunch of binaries, essentially, that come with like sometimes NDAs, a bit of explanation, header files and licenses and all that. And then if you are a vendor making laptops or something, you can take that and create your own platform with it. But those are all just binaries, so you don't actually get to understand the hardware underneath. So essentially, you can imagine you have like a fancy framework around that stuff that just calls into binaries, passes information, and hopefully it works, right? So if you run into issues with that, unfortunately, it's very, very hard to get, really to know how things went wrong or something. You would need to call support or whatever. And depending on, how big you are, like let's say you're Google, you can probably reach an engineer directly. If you're not Google, but I don't know, a very, very small OEM making a handful of laptops, then yeah, you get the idea. Anyway, so I don't want to do that sort of stuff. I work on firmware, a different project that is called Orboot. Who has actually heard of that project before? I'm seeing a handful of hands. That is cool. Yeah. So those who do not know, firmware in Rust is what Orboot is. So Rust, the programming language, is what we took at some point and said, hey, let's actually see if we can do that. And we effectively just forked Coreboot at some point. That was, I don't know, 5 or 6 years ago. The first commit was remove all the C code, so rm-rf src, make a commit and say, hey, we're starting over now, and then bootstrap the first tool chain. And over time, we tried to develop in a few directions, and nowadays we're mostly on SoC platforms. Essentially what you find in like single board computers, like TV boxes or phones or, that sort of stuff. But you can also put it in laptops nowadays, like the M&T Reform laptops, for example. They're also based on SoC platforms. So far, we don't have too much, right? So essentially, there is just a handful of people working on this sort of stuff. So yeah, it really takes some time to get there. And I will just briefly walk through the platforms that we already support. The first one that I did was the Allwinner D1. For that one, we had a dump of assembly for the DRAM initialization that was provided as open source code, right? I don't know about you, but I don't think assembly is like the nicest thing to deal with. So somebody took a lot of time and, I don't know, a clear mind or something, and translated that to C. And then I took the C code and translated that to Rust. And for whatever reason, it sort of worked in the end, which I'm very happy about. So I have a handful of very, very small computers now that I can actually fully operate with my very own code. That's very cool and rewarding. The next one I looked at, and that is now from a project that I'm going to talk about briefly, the JH7100 and 7110 from a vendor called Star5. You might not have heard about them, or maybe at some point. They are making RISC-V chips. And actually the D1 was also a RISC-V chip. It was sort of the first one that was very, very easily approachable because Allwinner already has a very, very nice community around them, so many people know that stuff, and it was also very cheap. You can still buy them today, by the way. Yeah, so this is now a new vendor, Star5, and they were part of the development board program that we have at RISC-V. So RISC-V, the instruction set, we have a large community around that sort of stuff, and you can apply for, getting a handful of boards so that you can develop your software on it. And that's what I did. And we'll briefly talk about how that went for me. But yeah, briefly the other platforms I did. There was the Softgo SG 2000 and 2002. Those are very, very small SoCs, mainly like targeting, surveillance equipment and that sort of stuff. So they have like, little amounts of DRAM. And yeah, translating that code was mostly straightforward, I would say. I got it just working. Then we have the SpaceMid K1. There is a few variants of that. There is also a rebrand. If you have followed the news and looked for RISC-V single-board computers, you might actually have heard of them a handful of times by now. You can get a handful of boards today, and they are featuring 8 cores for processing, quite some gigabytes of RAM, and for whatever reason, I actually got that stuff to work. The issue with that was there is essentially open source code for it in a project called U-Boot. U-Boot is like, let's say the main firmware that you get for SoC platforms nowadays. But there was some closed source code in it, which was essentially 1,000 bytes in a header file. I took that file at some point last year in summer. I started, and then I, step by step translated that code, and was very, very fortunate. That was very, very straightforward. So we're not going to talk about that today because we want to look at some more complicated stuff. The Kana and Kenwright K230, that was a very, very simple one. I actually just did that this year at FOSDEM. I was sitting there 2 days. We had like a pre-conference, let's say, with a community around open source firmware, and it just took 2 days to translate the code. Very awesome. There 2 days, good experience. Like, and I can actually take the thing now. I can just plug it into my laptop. It powers on within 3 seconds, and I have a running Linux kernel, all with my own code now. I know, featuring today, we're looking at the Rockchip RK3566 or 68. They're essentially the same thing, just that the 68 is like, a bit more powerful. I think has a few more peripherals, but otherwise they're very much the same thing. And yeah, now I'm going to briefly talk about how it went for me when I got started with the JH7100. So, the DevBoard program and everything about RISC-V was suggesting like, there is open source stuff we're going to do here, right? So I'm essentially in a very weird position now because I need very low level and detailed documentation. So I asked for it. I was writing this email here. That was 3 years ago in August. Essentially, I was saying, well, I don't actually have any documentation available just yet. So what I can find is some C code. It's very messy. That's being judgmental. So to be fair, I'm not a very, very good diplomat at that point. Whatever. So I was just asking for anything I could just get and more details. Thanks. Well, there was a bit of back and forth, so what I did was I added some more pressure. I was asked for more details, so I said, well, what I need and what I figured out so far is this. I found there is a vendor called OpenEdges. From them, they bought the DRAM controller, and well, I couldn't actually find much around that sort of stuff, so I asked for documentation on that specific part. But I said it would be a very big plus because I already know that, they don't actually want to provide that information, in many cases, because I don't know. It's a bit of a tough field. We're going to talk about that briefly now. Yeah, a few days later, just a week later, I wrote another email being a bit more direct, saying, hey, please reach out to the vendors you bought from. Can you just, make it happen so that I get some information? And guess what happened? Did I get the documentation? Well, so far, this is what I had. I had this image from their website. Okay, so this was my understanding of everything that is going on there. A handful of acronyms, and actually didn't know shit about DRAM. So a few days passed. I got another email with this. They offered me a so-called NDA, a non-disclosure agreement. If you think about it for a second, I want to do open source work, and they want me to not disclose information. So the problem is, if I want to provide that documentation, I would already be breaching that NDA, right? So that doesn't really work. I said, well, it's sort of a dead end, and my reply was, well, this has been sitting in my inbox for now, I don't know, that was 4 weeks later. I didn't really know what to do with it. I'm not a lawyer after all. I don't even understand all the legalese and shit. And I was saying, well, if you want to still provide the information, please put it in this repository here. That's where we keep it. Thanks. Anyway, back to translating C code, because unfortunately we didn't get any further with this. So yeah, a few years ago, end of 2022, when we had the remote events, we had the Fireshong stage, and that's where I presented the resulting work from what I did then over a handful of weeks or month maybe. I actually got that stuff to work. I only had to translate 4,000 lines of code that I didn't understand very much of, except for seeing a few, like, I don't know, there's lots of values being copied around. There were actually quite some comments in there, so if somebody is a domain expert in DRAM, they might actually understand it a bit more. I tried to add some understanding myself, like resolving some of the many acronyms. There is unfortunately lots of magic values in there, so you can think like, things that might be measured in a laboratory or something, with equipment I do not get my hands on because it's just way too expensive. So, I'm just a hobbyist myself doing this sort of stuff. I'm not employed by, I don't know who could just afford the equipment. And well, about half of the code I figured is actually just writing zeros somewhere. That might be necessary, might not. In the original code, it was very inefficient. So yeah, I was constructing a few loops here and there to make it a bit simpler. And still ended up with 4,000 lines of code. I don't know how that went. But yeah, you can imagine. That wasn't like something I did in a day or two. It was actually a few more. And then came the news. This chip is no longer being produced, unfortunately. Well, I figured that was sort of a prototype anyway, and there is a successor for it, the JH7110. I'd already anticipated that, right? So in one of my emails I actually wrote, hey, I'm anticipating if I get the information how that sort of stuff works, I can also reuse that information for another implementation later, because you will probably stick with the same part. That's actually very common for vendors, so they don't have to rewrite their code or something. So they usually try to retain a lot and then just modify things to, I don't know, make a more specialized processor, or increase the clock speeds or something, or I don't know, get the next version of the actual processing cores or something. But everything around it, often is very much still the same, like how everything works in a way. Anyway, so yeah. If you want to look at the presentation from Fireshong's, down there is the link again. That one is unfortunately in German, but the slides are in English. Anyway, meet the power of recognition. If you, look at those two pieces of code here, on the left-hand side we have the code for the new chip. On the right-hand side it's for the older one. And if you roughly look at the registers here, so you have a base address here always, and then you have an offset. They define the registers, and if you look at that, it's actually the same thing that you see here. And if you look at those values, you see they somewhat differ, but they're roughly similar in a way. Sometimes a few bits are just dropped or differ a bit. Like, for example, here we have a 1, 0, 3. Here we have 0, 0, 1. But otherwise, we also got the 4 here in the beginning, and so on. And I saw that actually all across the code base. Now, the only issue was, it was actually a completely different code base. So what you see here on the right-hand side was, custom code from the vendor. On the left-hand side, you see something that was integrated into U-boot, also using, some of the U-boot features and macros and all that sort of stuff. So it had a completely different structure. I translated the code that was coming from U-boot just as it was, and the same on the right-hand side. We have both an OR-boot now. If you look at that and you want to understand this controller a bit more, just keep that in mind. It's essentially the same thing. Anyway, down here are the two repositories actually. So the first one is the U-boot fork they did for the successor chip, and this here is the older implementation for the first chip. All right. With that, let's see how that actually works. So let's translate some code, but we're not going to translate C code now because that would be too easy, right? We're going to look at assembly now. Well, actually, we start with the binary. So the thing is with binaries, you first need to figure out how they would actually run. You need to know, in which address space they run. You might need to know the instruction set a bit more in detail. With the board I looked at here, or the chip, I was actually already aware of all that stuff, so I knew it was an ARM64, right? So it was also running in the 64-bit mode. It was little endian. I knew it was actually probably based on something that is, just written with like a simple C environment and so on. So, I could just set my tools that I'm using. But let's actually first talk a bit about tools. Who recognizes any of these logos? Let's start with the one in the middle. Who knows it? Everybody knows it, sort of. That's Ghidra. A very nice tool. It's for disassembly. It's for decompiling. So you actually, get from the assembly code that was recognized, you get something that looks a bit like C code. Sometimes you can take it right away. Very much often, I actually need to, think a bit more about it and adjust a few things here and there. But it's a very, very good starting point. There is other tools you can also use for that, but Ghidra is the open source one, so you can just take it for free, thanks to the NSA. Otherwise, there is also like Binary Ninja or IDA Pro, the more expensive ones. All right. There is a website I found, Shellstorm. It's somebody's blog. That's actually also very nice. It's an online assembler and disassembler. And so you have two text fields. So one is for assembly, one is for disassembly. And you can just drop very small snippets in there, choose your target, like ARM64, for example, and so on, and say, compile this or decompile this. And then you can understand what, how you would decode an instruction, for example. A very, very handy tool. The next one is the logo on the left. Who knows the thing on the left? I see one person. Okay. Except for you, let's everybody have a guess what the name of the project might be. Here's the hint. What do you see in the picture on the left? Yes, that's Unicorn. Unicorn is actually pretty awesome. It's basically on top of QEMU, the very well-known emulator, and it's something that you can just instrument. So you can say, hey, Unicorn, load some code into this memory region here, put some data in those registers here, and now run this code, and then you can read out the registers and see what the result is. That's very, very helpful, because I often have that case that I'm looking at snippets of code, and I have a rough idea what values are the inputs, and I want to know what the result is. But sometimes the code is a bit weird, or it might be using some ARM instructions I don't really understand or something. Maybe the translated code is not really very helpful for me. So I sometimes use it for that. And it actually already saved me a handful of times. Because unfortunately, when I was reading ARM documentation, sometimes I could not fully understand everything that was going on, but it didn't matter for me because I only wanted to know the result. So I just needed to emulate that code. And that's what you can just do here. Now the last one, that is more like a goodie. It's not directly used for disassembly or something. It's a different tool. Any idea what that could be? Does anybody know? Okay, you don't. It's the tail of a mermaid. Mermaid is a very nice tool for diagrams and flowcharts and stuff, and that's actually what I do a handful of times. So when I'm analyzing stuff from the disassembler, for example in Ghidra, you can also get a flowchart. So you can say, hey, show me the control graph. That's what's usually called, and then you would see like a very, very long list of small snippets and things that call into each other, and you see the ifs and the elses and all that stuff. You can follow along very nicely. But that's the direct outline. You might actually want to digest that a bit and have your own. Sometimes I just make a few notes in a text file and just do like indentation, like this function here is calling that function and turn that one, and it's also very simple. But if you want to provide some information to other people, it might actually be very helpful to use that sort of stuff. It's actually not too hard. So encouragement to also look into that. So let's do some Ghidra here. That's the first thing I usually do. So I start looking at the first disassembly, right? So I load the code, I say disassemble the code, analyze it, and see if you can find some functions. And very, very often that actually works very well. Let's just say most of the code I looked at was actually never obfuscated or anything in a way, right? So it was really just provided in binary form with a license around it. So it wasn't meant for not being analyzable, but just for saying, hey, we would like you to please not look into this. If you look at Intel's licenses, for example, that's sort of what they say. You can use it, but please don't take a closer look or something, right? That's roughly the license. And then there's the matter of free distribution. But yeah, I want to have my own translation, right? So yeah, I actually look at that stuff. So yeah, that's what it looks like. And usually you can find something very easily if the firmware is printing some strings. So, you know, strings are just data, and usually a disassembler can just find, hey, there is a reference to something here. It can recognize strings, like, you know, you have ASCII characters and stuff that is very easy to recognize if it's long enough. And then you can see, hey, there is something that is being passed a string reference. That must be the print function. And yeah, that's actually the first annotation I did here, right? So I called the function printf already. Now the next question is, where is actually the main part of the code? Well, this here, you know, that's the very first few instructions that are being executed. It's actually very easy to find. So if you look at those two functions here, they just did some initialization stuff, like, you know, a handful of lines. And then this here was the main function returning some value, and it might also, you know, return an error or something. But yeah, that is the main function here. And you will maybe see this pattern occur a few times where there is like one big function that is being called, and then everything else is just printing an error, and that's it. All right, so I have some patterns now for you that we're going to look at, and the first one is this here. I'm seeing that quite often, actually, because that's sort of reflecting how hardware is designed. So in this instance here, we're acting on blocks. So you can imagine, like, if you know, if you design hardware, there is often the case that you need to you know, connect to something else somewhere outside, and you need to talk to it. And if, like in the case of DRAM, for example, you know, you have multiple pieces of DRAM and something, so you might actually need to have a few blocks which are essentially the same thing that is talking to the outside. And so you also need to talk to those different blocks, and that is what you see here. So this is essentially just a loop, right? In Ghidra it's now, well, it's decompiled as a do-while loop, but it's essentially like a for loop. You can also model it as a while loop if you want, right? The idea is always the same. You have something that you start with, at a few certain offsets you would do something, and that's the end of the story. So what is going on here is we have a starting point, you know, that just came from some earlier code. That was the base register that we started with, and then for each iteration we would apply a mask to the value that was already in the register. So that means that we're erasing some of the bits there, and then we add some new information from another value that was also provided earlier. So yeah, that's a pattern that you might see very, very often, actually. A very simple one. All right, the next one is this one here, also a very frequent one. That's what you see in hardware, like, you know, lots of times, not just in initialization code, but you might also see it if you look at drivers, for example, or something. There is very often the case that there are so-called control registers and the status registers. They can also be combined in a way, and what it essentially means is you write something in a register for triggering an effect, and you need to know when that effect has been applied. So what you would need to look at is the status bits or the status register. You know, it can be the bits in the same register also. And you see, like, you know, if a bit is cleared or if a bit is set, it can be either of those. And once that happens, you actually know, hey, we're done now, I can now carry on. That can be a bit dangerous, so you might actually do this here. Who recognized the problem with this sort of code? An idea? Okay, say it. Yeah. So, but what can be the issue with that? Yeah, it can take a lot of CPU time. You're very, very close to the answer, yes? Okay, just don't mind the annotation. So this here is now coming from Ghidra. Don't mind how the pointers are annotated or something. Anyway, so the brief answer is, so you were very, very close. This might take a lot of time, and that time could be forever. It might be that the condition for actually breaking that loop, that one here, never happens. And you know, you would just see that nothing happens, right? So you power on your PC and you don't see anything coming up on the screen or coming out of the console or something. So sometimes instead of this here, you might see an additional counter that is also running inside the loop, and that is then another breaking condition. And so you would have something like, I don't know, if a counter is at 1000 or something, exit the loop and print an error, right? So that way you can actually escape this sort of infinite loop that might, happen in practice. But again, in practice, this is actually very, very often okay. But yeah, you will really need to know that it's okay because, let's say you make a typo here, right? So let's say you actually took the wrong register here. And in the worst case, this might be, might just be run under certain conditions, and you cannot actually test all the conditions of your code very meaningfully. Sometimes it gets very, very hard. It might actually depend on values that are very, very dynamic. Then that might be an issue. Just keep that in mind if you see this sort of code. It's always good to have a breaking condition in addition. I actually looked at U-Boot because somebody told me there is also some open source code for the Rockchip chips, except for not that one I looked at, but for the predecessors. Does that look somehow similar? We have the two while loops that are never, actually continue. Well, there could be infinite, so this is essentially the same thing, right? So it's saying, well, some condition, continue. While the condition holds, continue, continue. That's just the opposite phrasing of this here. So yeah, it's essentially the equivalent thing. And the offsets that you see here, so in U-Boot, they just have them codified in these identifiers here. So they're actually just the very, very same thing. It's equivalent. What does that mean? I'm very, very lucky because I'm now looking at code that is very, very similar to other code. So I can always say, hey, I'm not understanding this part here. Let's actually see what the open source code does. Is it actually the same? And that actually also helped me a handful of times, as we're going to see in a bit. Next, we're going to look at data in binaries, because that is also a very, very frequent thing. I told you earlier that a lot of the code I translated from C was essentially just writing magic values into some registers, and I didn't actually know what that means. And you can express that like this. Let's make a very, very huge list of just registers and values and iterate over it in a giant for loop. That's what you can do, and that's also what the vendors do, right? But then there is also data structures where it gets a bit more complicated, and that is usually with configuration. So there is very often configuration that is somehow declared, right? Let's say you're saying what the DRAM type is, what the DRAM speed is, and some other hard-coded parameters. You can very easily do that on single-board computers because it's mostly just fixed parts, right? So you don't have the DIMMs like laptop sometimes or on desktop systems, but you actually have everything sorted on the board. So you can just use fixed values. And that might look like this here, for example. So this here is a list, right? So you can recognize this because I already did an annotation here. I was saying, I just called it uint2. It's essentially just two integers, right? And at some point I figured, well, the first one is always an offset and the second one is a value. So what we're doing here is we're going to, using that code here, we're iterating over a handful of registers and we're just writing the values to them, right? And the values are, well, I don't know where they come from actually, but they look very, very arbitrary, right? So if you do not know what those registers actually mean behind that, you don't know what those values are either, unless you have so much expertise that you sort of recognize, hey, this sort of range of values or this block of values might mean this and that, but you would need to be very, very deep in that topic already and probably have seen some information that you can unfortunately not disclose. Yeah, the other thing I was also seeing is, as I already said earlier, configuration that is often just one global set of data. There was something, that just caught my attention very, very easily. I was seeing this sequence here, 0, 1, 2, 3, 4, 5, 6, 7, 8, right? It's a nice pattern. That's how they mark the start of their configuration. Then there is a bunch of values, and that's actually not where it ends. Just imagine a few hundred more values. They just don't fit on the slide here. But again, I was looking at what is in U-Boot, and in U-Boot I saw, hey, there is a very similar thing. We have the same numbers again, 1, 2, 3, 4, 5, 6, 7, 8. And then we have this sort of mind-boggling here. And then we have some comments. So now we actually know what this sort of stuff means. Except sometimes I don't know what this means. D2, D3, I had no idea what that meant. I figured that it's actually DDR2 and DDR3, and then there's a handful more of that stuff. So that is the type of DRAM, right? If you buy DRAM, you know there is like DDR3, 4, 5 nowadays, at some point 6, that sort of stuff. So yeah, this is essentially configuration for all sorts of different parts. Unfortunately, this is how it is integrated. So it's essentially a giant U32 array. That means lots of numbers. And lots of numbers is not very easy to handle in code, so you would need to, I don't know, carve out things and stuff. And that's actually what they happen. I don't know why they do that, but it might be because hardware engineers, you know, doing that sort of stuff, they're usually not very much software engineers, so you know they sometimes have a bit of a different approach to things. So you know, always bear that in mind when you see code that looks really, really weird. Those might actually be people who do not have the software engineer mindset. And that's also why sometimes it's a bit hard to understand. Down here, this is actually the path to a header file, and this header file tells you the actual structures in there. So besides these comments, we have the actual data structures, and in the code you can then see, you know, some casting going on and some calculations and that sort of stuff. I must say, this is actually one reason why we're writing firmware in Rust nowadays, because it's very, very easy in Rust to, you know, define data structures and, you know, do checks at compile time. And we're going to look at a counter example, let's say. This here. I was looking at this in Ghidra, so it's essentially like if this and this and this and this and this matches this and that value, I was like, why would you do that sort of stuff, right? It looks super weird. So I looked at UWood again, and I found this here. There is something called index info, and that is always an offset and a size, but it's just 8-bit values. So maybe they thought, well, there is not much space that we have, so we need to be very compact for some reason. That's actually not really the case. So yeah, I don't know why they did that, but again, hardware engineers don't necessarily have the software engineer mindset, and actually figured that some of the values are even copied around at runtime. Yeah, it's a bit weird, but that's what it is. Anyway, so you can already see up here that I have some annotations here, like dot size and dot size again, and so on. That's where I partially defined the data structures in Ghidra, and if you continue doing that, you get this here suddenly. So there is a giant data structure. I call it head info. It's like, you know, the main information that you use for configuring that sort of thing. It's one of 2 big configuration parts, and that one has a lot of information, like a version number, something called global, which has a size, and something called DDR that has a size. So what was called D3 on the previous slide, I expanded that to DDR3 because, you know, it tells me more. And then there is all this sort of stuff, and this is now validating something at runtime that you could actually do at build time. So this is really just making sure that the code running here that has its configuration inside is actually configured correctly. But yeah, that is something that you could do clearly also at build time already, because there is no information evaluated at runtime that is coming from somewhere else to verify, hey, we're on this platform now, so we should have that configuration. No, it's really just looking at the very same configuration that was part of the build process. So it's essentially a check on the build process itself, which you might arguably call a broken build process. This is the original code. It's literally this here. It's just that, you know, this is the opposite phrasing of it. So instead of equals, there is a not equals, not equals, not equals, yada, yada, yada. And if any of those conditions doesn't look good, then we would print an error and escape here. And otherwise, you know, you would continue with the normal code. And what Ghidra did for me was essentially the reverse, which might be the result of how the compiler, you know, decided to actually phrase it. Yeah, those are sometimes minor optimizations. So you might have something that actually occurs very often, that you have something in the source code, and then the compiler, you know, sort of just turns the logic around so that the control flow, you know, makes a bit more sense for it or something. You know, there's heuristics and stuff. Not too interesting right now, but, you know, just keep that in mind. You often have this like switch off logic, but it's still the same behavior, of course. Now about data structures. So it's actually not very easy to figure out data structures. If you want to understand data structures in disassembly, that means you need to sort of see that there is like lots of references to some base object. In a way, you can recognize that by looking at, hey, there is an address here, and it's used very, very frequently, and then they add numbers to it. That's what it looks like in the original code. In the original disassembly, right? And if you can actually define a type for it, then you get this sort of stuff here. So I defined, a struct type, and the struct is, I just call it DDR params. There's actually two of that in reality, but yeah, let's neglect that for now. And it has certain properties like ODT on slew rate, ODT off slew rate, and a bunch more. You don't actually see all of them here. It's just because not everything is used in this code here. But yeah, so this is now actually very, very nice to read again, but getting there is actually very, very hard. Fortunately, there is now some people who actually looked into that stuff more and more, and they are trying to come up with plugins or extensions for your decompiler that can infer those types. What they cannot do for you sometimes is guessing, the semantics of the types. They can tell you, hey, well, you have a handful of fields here. What do we call those fields? Well, we just number them, right? So it's field 0, field 1, field 2, and so on. And then it's up to you to figure out what they actually mean. With very, very well-known certain things, you might actually even infer that sort of stuff, right? So there is some data structures that are very, very common, like the offset and size sort of stuff that I had earlier. That might be recognizable at some point, but yeah, when it gets to very, very very special domain sort of stuff, like in this case here, it's actually very helpful to know the data structure. Well, how did I know the data structure? Again, I looked at U-boot. So yeah, if that looks familiar, it's because it's actually the very same code, except for, again, the logic being a bit swapped here. So yeah, but if you look down here, for example, those 3 lines, they're very much the same lines that you also see here, except you have some some shifting and so on here, and it's assigned to this sort of thing. But that's just the result of the compiler, I'm sure. Yeah. I make some comments sometimes, so when you see those comments here, that's what I figured out thus far. Sometimes I actually need to iterate over those comments, right? So it's really not straightforward to do this sort of stuff. But yeah, after after a while, you actually understand more and more and more. All right. With that, you now actually already know a handful of patterns that you can apply if you do this sort of analysis stuff. And now you might ask, hey Daniel, so how does DRAM actually work? And the answer is, I still don't really know. But I did some research for you. So what I figured so far, I'm just giving a very rough outline of things that you can just find on the internet, right? So let's gather some domain knowledge. Let's ask Google. Now, actually, Google gave me a shit answer, but I did find a few other references from Google. So if you read the Google AI summary, there is a bit of nonsense in there. Don't trust that nonsense. Look at actual references like systemverilog.io. It's a very, very nice website. You might have heard of System Verilog already, right? So Verilog, or System Verilog in this instance, is a hardware description language, and that's what you can use, for example, to program FPGAs or something, and that's also used in silicon design and so on. And so they actually teach you how this sort of stuff works, like essentially a lot of stuff in hardware. And I was actually very, very happy to see this sort of stuff because I didn't even expect it. But yeah, fortunately, this is roughly how it works. You do some power up and initialization. That's actually what we're doing at large. But some bits need to initialize, I don't know. Then you do some calibrations, and that's for impedance at some point, and data lines. So if you imagine DRAM, there is like a handful of transistors, and then you have like the actual memory cells and sort of stuff, and there is some very high-speed data passing around and all that sort of shit. And in order to get all of that to work, you need to do calibrations. That sort of makes sense to me, right? And in the end, you do this sort of stuff called memory training. That's where you figure out like more precise timings and sort of stuff. That's actually that stuff that is more proprietary from my so far understanding. So that was the part that I translated for the K1 platform back then. Yeah. So the open source part was everything up here, and then this part was what I translated. Yeah, there is another handful of references that you can look at. Yeah, if you want to, highly encourage looking at this sort of stuff. What you will also see that there is tons of abbreviations and acronyms. I just listed a very, very few here. It's really just a very few. Somebody made a very, very nice sheet here with a handful more abbreviations even. Some are vendor specific. And then, if you go further, you will find, many, many more actually. But yeah, with the vendor-specific stuff, you always need to be a bit like searching for, I don't know, let's say code in U-boot or something, so that you get more of an idea. I figured this is roughly how DRAM is organized. This is a nice picture that I got from, again, systemverilog.io. I think they took it from a Micron data sheet originally. And roughly, so you have channels, right? So you have your DRAM controller, and then you have the actual DRAM parts, and in between you have channels, so that you can, address multiple ones at the same time. Then within the channels, you have the so-called ranks. So you have multiple chips that are actually in the same rank, and then you have the banks. So up there you see the bank groups, and in each bank group you have a bank, and eventually you have rows and columns, and in a row and a certain column, that's where you have finally one memory cell that holds 1 bit for you. And that's roughly it. For more details, you can read those articles down here, and especially the systemverilog one, again, that goes very much into detail. This here is a real-life controller. This is actually how it works. So I didn't actually tell you this earlier. I was always in the mind that, well, there is the memory controller and the memory, but there is something in between. It's called a PHY, the physical part. That is actually what you also need to talk a lot to. And unfortunately, I think that is even a bit more complicated. But there is a company that tried to sort of standardize an interface. It's called DFI. More on that very briefly. This is now from a vendor called Cadence. Cadence is one of the 2 big vendors that are providing, all those hardware peripherals and stuff. The other one is called Synopsys. I looked at one of their controllers, and that's actually the one I'm currently dealing with on the Rockchip platform. Unfortunately, they do not have a nice picture like Cadence, but whatever. They have a nice description. It's mostly marketing, blah, blah. But it does tell you something about compatibility, like which DRAM parts you can use, and JADEC standards. JADEC and DFI interface. DFI, what you saw earlier as well. Here's the unfortunate part. The documentation to that sort of stuff is behind a login. I do not get to have that because you would need to have, I don't know, you need to buy millions of parts and be a giant company in order to even get there, right? I don't have that. The JADEC standards that are involved here are also not public. Yes, question? Yeah, so yeah, that is true. So you can create an account for JADEC and access a bunch of things, but not those here. So those are actually a bit more expensive to buy. I think it's a few €100 or something, maybe 300 or something for one of those documents. Yeah. The last one, DFI. So this website here is, if you look at it, it looks a bit old. DDR5 that is actually coming from Cadence. They define an interface, and they also publish documents for it. Unfortunately, well, also not public. You would need to have a login, even to look at the About page, actually. I don't know what's going on there. I can tell you that you can find those data sheets anyway, and sometimes you also find the JADEC standards if you keep looking very closely. All right. We don't have much time left. I will just dump a few further thoughts now, a few more hints of things that I found. Number one, when you power on your machine, it's actually not the first software that is running, that you can actually define a software, but there is actually other code that is running before you. That is the so-called mask ROM. Sometimes you might need to look at the mask ROM. I wanted to look at the mask ROM for the Rockchip thing. The unfortunate part is, I was running the vendor code first that was doing the DRAM initialization, and then I could actually, add some extra code myself. Like I could load U-boot next, and then I wanted to dump the mask ROM there. there. Unfortunately, I couldn't because it was sort of remapped and I couldn't reach it. So what do? Instead of running the vendor code, after I had figured out a few things, I actually tried to read the mascrom right away from my own first code that was running, and that worked. So there you go. Now you see a bit of the mascrom. It's actually not very special here. So usually what happens there is also a few initialization parts, and that would power up a USB controller, for example, and try to read code over USB. Or it might be trying to read from a SPI flash or an SD card, that sort of stuff. That's what you commonly find. Sometimes it's like secure boot setup and all that sort of stuff. Another thing, something that really helps is the call graph. So yeah, what you can do here in Ghidra, for example, is you can say, hey, show me how all the functions are being called and sort of stuff. So you get an idea of the code flow from like a more rough outline. And yeah, as I said earlier, there is a very nice tool called MirrorMate, and you can use that to make your own flowchart. So here I just made a flowchart for you that is essentially documenting the K1 platform that I reversed earlier last year. So this here is actually the open source part, and this block here, the training part, that is the closed source thing. And yeah, I figured that there's actually not much to do there, and it just worked. A handful of people tried it on various different mainboards. Yeah, I was really glad about that one. It's actually, by the way, still up to people to maybe port that over to U-boot if they want it. Otherwise, yeah, I'm integrating that in Orboot. I actually already have the code, it's just not upstream yet. Then I looked a bit more into memory controllers. People told me that they're actually going in a few other directions nowadays, because one problem that we have is when we process data, we need to always look at memory, load something into the actual processing cores. That is already very expensive. Then we do some processing, then we write back some data, then we load the next data, and so on and so on. So we have a lot of ping pong, and that costs a lot of time, right? And that scales up if you do, I don't know, let's say AI training stuff, right? So you look at giant amounts of data. And people want to shave off some time by actually putting processing logic right by the DRAM controller. Maybe that is some more motivation to look into that sort of stuff. So this here is the controller here. That is also used in the JH7100. I don't think they have this sort of stuff. As far as I understand, not, but it might be. I don't know. Or maybe we'll find that in a successor platform that is coming out somewhat soonish, I guess. And the last thing I want to provide you with is a handful more references to look into. Again, when you look at the slides again later, you can just click on all the links. So all of them are clickable. And what I want to highlight here is, whoops, sorry. I want to highlight AMD here because they actually, they have their portfolio for FPGA programming, and they have a lot of information in there. Really, really nice to look at. Alrighty, and yeah, with that, thanks a lot for listening. And yeah, here's all the references. If you want to hunt me on Mastodon or something, you can find me there. The slides are the last thing here, that one. And yeah, I think we have time for like 2, 3, maybe 4 questions. And there is already a raising hand. No, that's the microphone. I'm looking into light, so it's a bit hard for me to see. All right, there is one question.
So since you've reverse engineered DRAM initialization flow for some of the Rockchip SoCs, do you effectively have a fully open source boot flow until the kernel? Because except for the mascrom, the U-boot is open source. The DDR initialization, I think that was the only blobs, right?
Mixed answer, yes and no. So, a very brief recap on platform design. So, many platforms are designed so that you also have, the so-called trusted firmware or something. There might be closed source code for that. So that would be, in the ARM range. They have this sort of extra code that can be used as services or, I don't know, for confidential stuff or something. I cannot talk about that sort of stuff because I don't know. I haven't looked into it. So I'm just interested in the DRAM stuff for now because that, enables me to, maybe already run the Linux kernel. I don't know about the, so in ARM there is the different, they call it exception levels. It's like the rings on x86, sort of, but still a bit different. Those are different processor modes so that you can do like, kernel stuff here, user mode there, and sort of stuff. I don't know how much I need to drop down to another exception level. It might be that it just works dropping down and then Linux can run. I think that will be the case. I must also say I'm not yet done with that stuff, right? So this is sort of work in progress. I'm currently actually running into an issue that I've been staring at for like 2 weeks now. Still haven't figured it out. I think I will at some point. And I'm actually very much through with the initialization process, and then I would already get into the training, from what I understood so far. So yeah, not making any promises here, but I'm actually very close. And I must also stress that I'm not looking at the highest speed initialization code. So there is, blobs for different DRAM speeds. I'm just looking at the one that is the smallest size because that's the easiest, I think, right? Because there is not that much code in there. But it might be that the other ones actually have still the very same code, but just more data. Yeah, I'll figure that out. But yeah, I'm still somewhere, let's say, sort of in the beginning, maybe in the middle. I'm not sure even. Right, another hand.
Where are the values stored when there's no DRAM? For example, when you don't store structures, which when you access memory, you need somewhere to store it.
Right, okay. The brief recap of how these platforms work. So initially, you do have some RAM, and that is the so-called SRAM. That is static RAM that you can just use right away. And that is where the mask ROM would load your code, whether it comes from an SD card, or in this case, I can load it over USB. It would just load your copy into SRAM and then execute it from there. So essentially, you would transfer a blob of data, let's say, I don't know, 50 kilobytes or something, and that's where you have all the code that is necessary to bring up the DRAM. Once you have that done, then, of course, you can load code into DRAM only. But yeah, earlier you can do that, yeah. Follow-up question?
In extension to RAM, what's the difference between the x68 architecture when you want to initialize it? Yeah, because there's no SRAM on the x68 architecture.
Right, so the x86, I don't have that much experience with that, I must admit. What I roughly understand is, that might actually be historical stuff only. There is a concept called cache as RAM, or CAR. If you look at the code in coreboot, you will find that in a handful of places. So essentially, they're just using the cache, which is effectively SRAM, for bringing things up. Yeah, I don't know exactly how that works, but it works. I mean, there has to be a way somehow. There's even, I think, for very earlier platforms, there is something called ROM-CC in coreboot, which is like, I don't know, it's a very specialized compiler to deal with that sort of stuff. Right, any other questions? Then, just before midnight, question? There's a hand, okay.
How do you, there's a huge problem like getting the memory maps for the source code, for the not source code, for the binary code. Like, is it, what's like your approach there?
Right, so memory maps are in part available usually in the manuals, so at least you get a basic understanding, right? So you know the base addresses usually of all the parts. Sometimes there are some which are not documented, or they are only in NDA documents or something. And what mainly is well documented is things like GPIOs, for example, or special system-wide registers and all that sort of stuff. But yeah, not the high-speed parts like a DRAM controller or a PCI Express controller or something. Those are often redacted or just under NDA. So what is my approach to doing that sort of stuff? It's very, very simple and stupid. So when I start translating code, I usually see, when things are happening in MMIO space, so we're writing to registers somehow memory mapped, I see there is some base address. I know the base addresses mostly, and then I know the offset. So I just call my variables, let's say, I don't know, DRAM controller 0054 for, you know, register 54, and so on and so on. And I actually did that for the RK3566 here. And then when I got to understand that it's actually the same controller that I also see in U-boot, you know, then I could actually name the registers at that point. But that was only for the controller. The PHY is actually different from the ones used earlier. So there I only have the numbers, and I have no idea what those numbers mean. I can, you know, only understand a few of them from looking at the code flow. Like when I'm seeing, hey, there is some polling going on here, I see that's a status register, right? So that's the few things I can infer from looking at that. But yeah, I also assume with a bit more expertise, you know, you might actually understand a bit more, but yeah, I'm not sure. Maybe I will understand a bit more in 5 years if I keep doing that sort of stuff, if it doesn't drive me crazy. Right, another hand. Oh, the microphone keeps bugging me.
Do you have any idea why they're polling something, or is it waiting on the file to do something?
Oh, right. Yeah, so the question is why the polling in the first place. It's really just the communication mechanism, right? So you let the hardware do something, and it's in many cases not done in just a single clock. So you can't rely on the next instruction already expecting that what you did earlier actually already had an effect. So you need to wait for the effect to apply. There's two ways of dealing with that. One is you use a known timeout. Sometimes vendors actually do that. So you see like a lot of like, I don't know, sleep 1, sleep 2 or something in their code. And sometimes, you know, they would just look at the status registers as you usually should. That's really everything behind it. Nothing really special about it. Oh, right. Yeah, so what actions might be happening there? I mean, if you already have open source code and it's documented, then, you know, you can just read what's going on there, right? So sometimes it's saying, I don't know, we're increasing the voltage here, and then we wait for whatever part is doing that to actually have applied the voltage. You know, sometimes it might be rising slowly, like from our perspective, it's very, very fast, usually like nanoseconds or something. But from the processor clock speed, you know, it's, I don't know, it might take a few clocks, right? And yeah, that might be what is going on. There are things like, I don't know, turning on a gate or something, or I don't know, changing a clock speed, all those sorts of things, yeah. All right, no more hands. And now it's actually past midnight. So yeah, thank you very, very much for listening, and enjoy the rest of GPN.